So again, there is no very robust meaning of converting one LP into other. Our basic principle would be I don't want to say same solution, but achieves the same purpose. Okay, and most of the time this purpose will be achieved. So converting one into another, let's say you want to convert A to B, or these directions, and this will be done so this is a map or a function or a process which converts, and such a way can be converted into So when you look at this, you should at least be convinced that if I can do this, then clearly instead of solving A, I can solve B, instead of solving B, I can solve A. Right? So this is probably the simplest way in which we can define two things are equivalent, but this is not general enough. It turns out most of the time what we need is we can convert optimal solution, and the other feasible solutions, even if you cannot convert to them, I don't care. Okay, and again, instead of same, it could be a well-behaved function. So instead of the output value p, you can get p plus 1 or 2p or p square, and all these cases, even though it's not the same objective value, you can get the previous objective value back. Right? So this is in some sense the meaning of converting one LP into another. Okay? And let me just show you two by examples which will make this thing clear. Okay. Yeah. So remember, I should write down the standard program. So you can have constraints like and the standard program is okay. Okay, this is not exhaustive in the sense that you can also ask how do you convert equality into inequalities, all that, but let's just see this direction, others are not very difficult. Okay, so first, do I care about min max? How do I convert into maximum into min? Just yes, just change C to minus C. Okay, so then this is fine. Okay, how do I convert AI transpose X less than equal to BI to equal to BI?
Something like again we have to take a
No, but you are putting an extra constraint that might not be there. Sorry?
You can add a dummy variable.
Yes. What you can do is you can say this let's say this is a jth constraint equal to bi. Okay. So is it so given any solution here, I can obviously convert it into a solution here. Whatever is left, I will put it in SJ. Given any solution here, it automatically gives me the same solution here, right? So here the equivalence is pretty tight, right? You can go back and forth easily. This is fine. And obviously this is either way, right? So AI transpose so I have taken care of both sides, right? What else can be different in the standard function? It could have strict inequalities. What do I do with strict inequalities?
SG is strictly greater than 0.
Sorry?
SG would be strictly greater than 0.
You haven't changed the thing, right? It is still now, but here there is problem, right? So how will you change Sj greater than equal to 0, greater than 0 to Sj greater than equal to 0? We don't know a way, okay? And this, so one thing would be that, we allow this kind of constraints too, but that makes the mathematics of linear programming much tougher, okay? So what we do is just approximate them by putting the equality constraint there. So we will just switch this to this to this.
And again add dummy variables for the same.
Yeah, if you want to convert to equality, then so once we have converted to this, then we can use the same route. Okay. What else could be different between these two programs?
To compress all the AI into a matrix.
Sorry?
You have to compress all the AI.
That you can do. But mathematically, what have we not seen? What is left? Notice that when I write this as a standard linear program, this greater than equal to condition is on the entire thing. You can have a linear program where your variable is just real, like the coefficients in the approximate degree case. Then what do you do? How do you deal with unconstrained variables? Very nice, yes. So the idea is, if you have an unconstrained variable, let's say this is an R, you can switch this to okay, clear? So now, given these small tips and tricks, it turns out we can always assume that our linear programs are in this fashion. Correct? Now, in some circumstances, this is a standard form which we want to deal with. This is very helpful. It turns out some people like that standard form. Do you agree that this is good enough? What do we have to do to prove that this is also a standard form? Right. So then I want to change this into this kind of a linear program. C transpose X is fine, X greater than equal to 0. Right? I can change. So what is going to be my new A prime and B prime in terms of A and B? Write it.
When you say a vector greater than other vector, do you mean every entry greater?
Yes, yes. Thank you. That's a good point. Yeah, it could have different meanings, but for us, X greater than equal to Y means for every similarly equality, similarly less than equal to. Okay. So if there were m constraints and n variables, what will be the dimension of, like, okay, how long will A prime be? Right. It is going to have 2m plus n constraints, right? And what will be the things here? Here, okay. So when I do this with this A prime and B prime, I get generally when we are solving things, this standard form is nice. When we are talking about convexity and all, this standard form is nice. Okay, so don't get hung up on this is the standard form. Okay, the important point is, as required, we can simplify and we can just worry about one particular kind of standard form. That makes our life easy. Suppose you are given these sets from 2 to the power n Boolean strings. Okay, these are not elements, sorry. These are subsets from 0, 1 to the n. Clear? Okay. And you are given this LP. So, the variables so constraints are over these this is the linear program given to you. Okay, there are some m subsets. You want to maximize ux plus vx such that ux minus vx is less than mod of ci. What is the value of this linear program? What can you say about this linear program? This is what you want to solve. Can you utilize those tips and tricks or convert it into an equivalent LP? Okay, this is a hint. Can you convert it into an equivalent LP and suddenly the answer will pop out? Anyone knows the answer to this?
It's kind of trivial.
Okay, good. Anyone else? Yes, very good. So, two people see it. Let me just write it in a different way and then everyone will see it. Okay? Okay? The thing to notice here is we have this substitution. Given ux and vx, I can get zx and yx. Given zx and yx, I can get ux and vx. Right? So then this change of variables is fine. I am only converting one LP into another equivalent LP. But now if you look at this LP, the thing which you are maximizing is different from the thing at the constraint. Right? So that means you can get the value of Zx as high as possible. It doesn't matter. So as pointed out, this is unknown. Right? So this is kind of these tips and tricks, even though they are not very ingenious, they are not very difficult, but they are really, really useful. I'm not going to devote much more time to it. You will see exercises, you will see like most of the applicants, you have to do these tips and tricks to make your LP look nicer. Okay. What I'm trying to emphasize here is that even though these are simple tricks, you shouldn't overlook them. And you should understand what is required. Once again, the bigger philosophy is, I can solve this if I can solve this. But then most of the time, it will be achieved by saying, given a solution here, I can convert it into a solution here. And if you want it to be equivalent, given a solution here, you can convert it into a solution here. Okay? Keeping the objective value in a nice fashion, probably a nice monotonic function or something. This allows us to go between different linear programs, and suddenly your knowledge about the linear program increases. Right? So I think you will agree that some people saw this to be unbounded, but this makes it suddenly very, very clear. This is unbounded. Right? So this is part of our tool set when we deal with linear programs. And just to take the last example, I talked to you about dual, right? And what was the idea? You are given a linear program, there is something called a dual which is very nicely related to your original optimization problem. Okay, they obviously have the same value, not just that, they are very deeply related, and we will explore this. But before the dual, before we go into that, I want to talk about the dual of the approximate degree problem. You remember we did the linear program. What was the linear program? Right? So in general, whenever we see a linear program, we can always ask, what is its dual? And understanding the dual gives us lot of information about understanding the primal. That you will see throughout this course. But what I want to do is, I will, in this case, because we are not familiar about how to take the dual, I will give you the dual and I want you to simplify it. Okay? So, you remember we had a function which we wanted to approximate. This was a correlation. So this is the monomial xi1, xi2, xik, whatever is in the S, right? And this is equal to 0. Clear? This is a linear program. What it represents, everything is at this point not clear, right? What are the variables here? Psi1x and Psi2x. Okay? So there are 2 times 2 to the power n variables. And then these are the constraints given. How can you simplify this? And I think what you are also given is, yeah. Now, if you want to simplify it, let me tell you, we don't have much time, but one thing would be, I see the psi 1x minus psi 2x many places, right? So let's just replace it by a single variable. So this is just to tell you what kind of tricks you can play in this equivalence things. So I will just say this. Okay. Now at this point it seems like I have made more variables than what I had, right? I had 2 times to the power n variables, now I have 3 times to the power n variables. And the idea should be, we should be able to write this in terms of psi. One way is that I define psi 1x plus psi 2x some other variable, but that doesn't help. I will give you 1 more minute, we don't have much time, but can you think of some simplification here? See, what you can do is, you can think of psi 1x and psi 2x. We are interested in their difference, right? Can we make sure that at least one of them is 0? Okay, so let's say my psi 1x and psi 2x, I'm just talking about 1x. Suppose this one was the case. Okay, I make it 3 minus 0. Okay, how does it help me? My psi 1x minus psi 2x remains the same, and this thing is now I have much more control over this. What I can do is, remember, here I want to maximize, right? So if I do this, then this thing becomes smaller than 1. I can scale these things and get a better value here. This is not easy. This is probably one of the more difficult conversions. But okay, and this is possible because this is an optimization problem. This you might not have seen in equivalence. What we were doing was equivalence, yx equal to zx. But since we are optimizing here, we are only interested in the optimal solution. What we can say is, if these were the values, it's much better for me to consider it as 3 minus 0, and then you know that sum total here was 5, here it is 3, I will just scale everything by 5 by 3. So this allows me, so or yeah, even this is equal, these constraints, but this allows me to have this satisfied but increase the objective value. Okay, so and if that is the case, you can actually replace it So you get a very easy program in the end. Again, this is not written as a linear program, but it's easy to understand what it means. And then so I think I have not explained this properly. What I want is you think about this equivalence, otherwise we will do it again in the next class. But this is a very non-trivial equivalence. Okay? So take it as a homework, see if you can convert from here to here